Today, a tough concept. The mathematics is not too crazy here, but the concept is tough. So I'll try and work through it slowly and help you with understanding what we're trying to find here. Scalar projection. The following diagrams illustrate the concept of scalar projection of one vector onto another. So when we've got two vectors like this, u and v, when we talk about scalar projection, we want to know how much of one vector is in the direction of the other vector. That's the physics version of understanding it. We want to know how much this first vector pulls straight along the second vector. The wagon examples is a good one here. If you sort of turn your head sideways here and imagine that bottom vector as the ground that you're pulling the wagon along, and the angled vector is the force that you're pulling on, we want to know how much that force is actually pulling the wagon forward. There's a visual understanding of this too, which is it's the exact same thing as the shadow that one vector puts on the other, as if it was straight down. So let's just watch here. So if you got u and v here, we want to know how much of that u vector actually operates along the v vector. Or, if you want a visualization, imagine what shadow do we get on the v vector. Do you see that red shadow that we got there? Well, that's the big idea. If you sort of follow that, then you're probably in great shape here. That's called the scalar projection of u on v. We can also do a scalar projection of a on b where one vector is longer than the other. And when we do that, all we mean is along the line of b. So just because it extends past b, we can have that shadow go longer than the actual surface there. So the analogy isn't perfect here, but if one vector is longer than that, it's no problem. It's just along the line of v. So to rephrase from the first example, u projection on v means how much of u is along the line of vector v. And so there's the vector projection of a and b. It's actually longer than b, and that's okay. What if the angle is obtuse? Well, that's okay too, because my new definition actually helps with that, is to say, when we say g projected on h, we mean how much of g acts along the line of h. In this particular case, it acts along the line of h right there, and you actually get a negative answer. So calculating the scalar projection. To calculate the scalar projection, we need that angle in there. So the scalar projection of a on b, it's actually pretty straightforward. Cos theta is the scalar projection of a on b, that red line, over a. And so if I want to calculate scalar projection, it's just a cos theta. Pretty simple calculation here. Some notes about the scalar projection. The scalar projection is a scalar value. That's why it's called scalar projection. You're going to get a number here. You're going to get a length of that shadow, like a 5 or a 2 or a 7.8, whatever. If the angle between the vectors is acute, you'll get a positive number. If the angle between the vectors is obtuse, the scalar projection is negative. And if it's 90, you'll get a 0 here. So if you get a scalar projection of 0, it means you've got a 90-degree angle. It means the first vector was not acting along the second vector at all. Or if you want the shadow thing, it was projecting straight down and you didn't get any shadow at all. There are other ways to calculate the scalar projection. This is the simplest way if you're given the length of the vector and the cos theta. But sometimes you're not given that length directly. And so there are other ways to come up with it. Or if you're given the, you're not given the angle directly. So what we note in the thought bubble there is that a dot b is magnitude a, magnitude b, cos theta. And if I solve for cos theta, I get a dot b over magnitude a, magnitude b. And in my first formula, I just replaced cos theta with that a dot b over magnitude a, magnitude b. And now I've got a formula that doesn't include theta. So if you're not given the angle, this can be a little faster. But if you're really looking, you can see that those magnitude of a's will actually cancel. And so on this other version right here, this version right here is a better one when you're not given the angle, because it cancels out those magnitude a's. And all that's in there is magnitude b, which is nice. One way to write scalar projection, all the way along we've been saying scalar projection of a on b, but you can use this symbol here, and it's kind of handy to write scalar projection. And it sort of reminds you what's going on here. You want to find out how much of the vector a is on vector b. Are a projection b and b projection a equal? No. The shadow of one vector on the second doesn't have to be the same as the second on the first. And you can see that in the formula here. This has magnitude b in it, but it doesn't have magnitude a. If I go to do it the other way, I'll get the other vector in there. And so if a and b aren't the same size, you can get different answers for the two. Oh, some examples right away. If u, magnitude of u is 12 and magnitude of v is 7, and the angle between u and v is 54, determine the scalar projection of u on v, and then of v on u. So I'll do first u projection v, with these absolute value bars to indicate its scalar projection. And to get that, what I need is magnitude u cos theta. So I get 12 cos 54. And when I type in 12 cos 54, I get 7.05. Now I'll do v onto u. In that case, it's v vector, the magnitude of v vector cos theta. So this time instead, I get 7 cos 54, and I get 7.05. Oops, I wrote one of those wrong. No, that's 4.01. 4.1. Not the same. I said the same number out loud again there. Okay, so you can see that because the magnitude of the vector being projected is in the equation, you're going to get different answers if those two magnitudes are different. There's an example where you're given the angle. If you're not given the angle, oh, look, and 3D as well. This can be done in 3D, no problem. Imagine that for a second. These simple formulas allow you to project one 3D vector onto another 3D vector. The version of the formula I want to use this time is vector projection of A on B. I'm going to use this formula instead, which is A dot B over magnitude B. That's the better formula to use here because they don't give me the angle between them. I could go ahead and find the angle and use it, but this is much faster. And then A dotted with B, let's see, negative 5 plus 18 minus 14 over square root of 1 squared plus 6 squared plus 7 squared. So that top I get, negative 1. And the bottom I get 36, 75, 86. And that, to be honest, sometimes we don't get too excited about the radicals in this chapter, but if you really want to get it technically right, you really should get that radical out of the denominator because it might do some simplification after that. This one doesn't. Okay, so that's vector and scalar projection. So that's scalar projection, and we'll talk about vector projection in a little bit. So scalar projection is how long is the shadow of one vector on another, or how much does one vector pull in the direction of the other. Okay, now some things on direction cosines and direction angles. Now that we've discussed scalar projection, we can develop an alternate technique for describing the direction of a vector. This method focuses on the direction angles of the vector. So this diagram is not bad. It sort of helps to see what we're trying to find here. Is we got some vector u sticking out in space like that, and what we want to find is the angles between that vector and each axis. So alpha is the angle between the x-axis and the vector, beta is the angle between the y-axis and the vector, and gamma is the angle between the z-axis and the vector. And the direction cosines are very helpful here because if you just project that vector onto each of the axes, you find that you can just do cosine of each of these. And cosine of alpha is the A, the x component of the vector over the magnitude of u. Cos beta is B over magnitude u, and cos gamma is C over magnitude u. Very simple formulas to indicate that when this vector is projected onto each of those axes, all we need is the length of that vector in that direction. So, not easy to visualize when you first see them, but nice and easy to memorize to find the angles between them. And that's the reason they're called direction cosines. If we want to find the direction angle, then we just use these cosines to do that. Notice that cos squared alpha plus cos squared beta plus cos squared gamma equals 1. It's very similar to the Pythagorean identity. It just works in 3D. If you take take each one of these, if you look here, and you square them and add them together, what you get in the top is a squared plus b squared plus c squared, which is the Pythagorean theorem in 3D, and things will just cancel out nicely and you get 1. Try it out. It's really fun. Just take those three things right there and just square them all and add them up, and you'll see you'll get 1 pretty quickly. Okay, so it says determine the direction cosines for this vector. So this seemingly random vector sticking out in 3 space, and what we want to find is the direction, cosines, and angles. To do that, we need first this magnitude of this vector. So first I'll find the magnitude of this vector, which I'm going to call u. And so I just need the Pythagorean theorem in 3D. I got to go negative 2 root 2 squared plus 4 squared plus negative 5 squared. Let's see, 4 and 2, that's 8 and 16 and 25. Root 49. Oh, isn't that nice? 7. The magnitude is 7. So if I want to find cosine alpha, the angle between this vector and the x-axis, I use the x component and put that over the magnitude of the vector. That'll be the projection onto the x-axis. Then the projection onto the y-axis will be the y component over 7, which is the magnitude. And then to find the cosine of gamma, which is the angle with the z-axis, it's negative 5 that's going to be projected on the x-axis, or onto the z-axis, and I get 7 there. Now, to find the actual angles here, I'm going to actually put an extra step in here. If I do cos inverse of 2 root 2 over 7, what I get is 66 degrees. But this cosine's negative, so actually alpha is 180 minus the 66, which is 114. I don't want to get too carried away with trig here right at this particular moment, but that has to do with the cast rule and that this negative was in the second quadrant, so I first had to find that related angle first. This next one's positive, so I don't have to worry about stuff like that. I can just do cos inverse of 4/7 and find that angle with the y-axis. Cos inverse 4/7, I get 55 degrees. And this one again, I first got to find the related angle, cos inverse of 5/7. That is, find the related acute angle, find the positive quadrant angle, which is 44 degrees, and that means that this gamma is 180 minus the 44. This gamma is 136 degrees. It had to be obtuse because the cosine was negative there. Now vector projection. The only difference here is we're going to turn the scalar projection into a vector, and let me show you what I mean by that. We simply multiply the scalar projection by a unit vector in the same direction. So here's the scalar projection. This is the picture from earlier. And notice it's just a red line. There's no arrow on it. We were just finding the length of that shadow. For vector projection, we want to actually find that length of that shadow with an arrow on it saying in this direction along the v vector. And it's already been described here what we do. We multiply the scalar projection by a unit vector in the same direction as the vector we want to go. So first we say, find a unit vector along v, one that's exactly 1 long, multiply it by how long we want the vector to be, and then you get your vector projection. Notes on vector projection. The vector projection is a vector. We actually want to find a vector this time. So we find scalar projection, scale it, and then multiply it by the vector. The unit vector. The vector projection acts in the same or opposite direction as the vector in which the projection occurs, depending on the angle between the two vectors. And we write it with a projection B like this without the absolute value bars, because now we're talking about a vector, not a scalar. Calculating a vector projection. We multiply the corresponding scalar projection by a unit vector in the same direction. So there's a projection B in the picture. To find a projection B, what we do is we do A dot B over magnitude B. And what that is the scalar projection from the earlier in the lesson, that A dot B over magnitude B. If you look back, scalar projection is just A dot B over B. So we multiply the scalar projection by a unit vector in the same direction. So this one here, we take the vector B that we're projecting on, and we divide it by its own length, and what we get is a unit vector. So that vector will be length 1. The scalar projection will be the length we want, and then we get a vector along the direction we want. Now that's one version of how to calculate this. You can collect the magnitude b's in the bottom and get magnitude b squareds. And magnitude b squared is b dot b, and this formula is beautiful. It's just a modified form of that because it's very, very convenient for finding vector projection. Tough to know that vector projection formula. You've got to sort of memorize it the first time through. But how is it used? If you want to find vector projection of A on B, you just use A dot B over B dot B times vector B. And if this is all a little confusing, let's watch what happens here. A dot B, let's see, I get 12 and negative 5 is 7. I'm doing that all in my head. B dot B, I get 9 and 1 is 10. And that's all in the direction of vector B. So the vector projection is 7/10 of this 3, negative 1. So the 7/10 is the scaling factor we have to do to make it the right length. The scalar projection was a certain length. This vector was not the right length, but the 7/10 scaling factor does make it the proper length. And if that all is like, wow, it does all that, yeah, it does. That's exactly what this thing does, is it finds that exact scaling factor we need to make the vector 3, negative 1 the exact right length to be the vector projection. See, this vector B was, see, look up this one. This was the, if you want, this was the 3, negative 1. And then 7, it was too long to be the vector projection. You can see in the picture, the vector projection matches up here. It was shorter, and the 7/10 is the exact scaling factor you need. Okay, well, folks, I got to tell you, on a scale of 1 to 100, if you understand scalar projection more than about 40 or 50 the first time through, you go through that lesson, that's pretty good, actually. I'd be pretty excited by that because it's a very difficult idea. The math isn't too bad here. Try some of the math, and as you're doing the questions, as you're doing the calculations, some more of that ideas of scalar and vector projection will come through, and then come back and rewatch the video and try and reaffirm those ideas.